So first we're going to start with strong acids and strong bases because they're more straightforward. There are 7 strong acids. They are hydrochloric, hydrobromic, hydroiodic. Those are the 3 binaries. And then 2 more chlorics, so chloric acid and perchloric acid, as well as nitric and sulfuric. So those are the 7. You do need to memorize them. Anything else is a weak acid. So if you know those 7, then anything else will be weak. And if you see a strong acid, you should be happy because they completely break apart, meaning that the concentration of the acid that you see is going to be equal to the amount of hydronium ion. So if I asked you to find the pH of a 0.1 molar hydrochloric acid solution, you should immediately recognize that that also means that the hydronium concentration is 0.1 molar also. So then you can do what you will to find pH. So keeping strong acids completely dissociate. That's like your key words. Strong bases are basically ionic compounds that have hydroxide, specifically alkaline metals and heavier alkaline earth metals tend to be strong bases. So they completely dissociate. So then I have, if I have an alkaline metal, I have the metal ion plus 1 hydroxide ion. And if I have an alkaline earth, then that means that I have that metal plus it dissociates into 2 hydroxide ions. So that means if I have a 0.1 molar, let's say barium hydroxide, then we should know that that means that my concentration of hydroxide is 2 times that, so 0.2 molar of hydroxide. So here we have perchloric acid. Our little ringer should be dinging. That's a strong acid, so then I know that my concentration of hydrochloric acid equals my concentration of hydronium, which is 0.04 molar. So then the pH is going to be the negative log of hydronium. So it'll be negative log of 0.04 molar. So that's a very low pH of 1.40. Here I have nitric acid, has a pH, so I want to find the concentration. So the pH equals 2.34. So the hydronium concentration equals 10 to the negative pH. So 10 to the negative 2.34. That equals 4.57 times 10 to the negative 3rd molar. So then that also equals the concentration of nitric acid. Great. Okay, last part with hydroxide. So I have sodium hydroxide. So that has 1 hydroxide there. So I know that my concentration of sodium hydroxide is the concentration of hydroxide. So I can find the POH. So POH equals negative log of hydroxide, which is negative log of 0.028. So the POH ends up being 1.55. So then I do 14 minus POH to find pH. So 14 minus 1.55 equals 12.45. So that's one way. You can also go from hydroxide to hydronium using Kw. That's another option. Here I have my hydroxide solution, but I have 2 of them. So I know my hydroxide solution concentration is going to be twice that of calcium hydroxide. So then I'm going to do negative log of that to get POH. And I get 2.68. So then 14 minus 2.68 is the pH. And that equals 11.34. So now we have weak acid. So anything that's not one of those 7 is a weak acid. And we'll show that the weak acid with water partially dissociates. So we get an equilibrium between hydronium and the conjugate base. So the difference with strong acids, we did a forward arrow. Here we have reverse arrow. And for weak acids, we have a lot of the reactant left over and a little bit of product made. So since we are in equilibrium, we'll have this new equilibrium constant, the Ka for acid, and it will be products over reactant. So hydronium times conjugate base over the acid. And we don't do water because it's a pure substance. So the larger that Ka means that I've produced more hydronium, which means that I have a stronger acid. So we're going to look at our equilibrium constant value, Ka, to see how strong our acid is. And we're going to look for high Kas equals stronger acids. So if you look here, strong acids, Ha here, completely dissociates forward arrow. So I don't have any HA left. I just have hydronium and conjugate base. No more acid is left in my solution. So strong acids completely dissociate 100%. Weak acids only partially dissociate, meaning that I have quite a bit of HA left in my solution, and look at mostly HA, and one of them happened to dissociate, for example. So really small ratio here for our weak acids. Here are some examples of weak acids and their Ka values. Notice higher Ka is stronger acid. So that means we have a weaker bond here between our hydrogen atom and its conjugate base. So it will be easier for it to be released. We have a polar bond. And over here, down here, something like an alcohol, it can break off, but not very much of it does. It's very weak, has a low Ka value. So there are a couple ways that we can express how strong an acid or base is. We talked about one, the Ka. So if the higher the Ka, that means the stronger the acid. That would be the same thing for base too. Higher the Kb, the stronger the base. So, but just like with pH and hydrogen concentration, it's easier to talk about pH. So we could also take the pK or pKa. So take the negative log of the Ka. And because that's really telling us the numerator, then the stronger the acid, the lower the pKa. Just like if I had a concentrated acid solution, the higher the hydronium concentration, that means the lower the pH. So same thing here. And so for Kb, I could do pKb, and so the stronger the base, the smaller the pKb. And just like we did before, percent ionization, that's the amount of molecules that ionize or dissociate when in water. And so when I have a higher percent ionization, then I have a stronger acid. And so for weak acids, if the percent ionization is less than 5%, we can make that assumption where if I have there my initial concentration of acid minus X, that's going to be basically equal to my original concentration of acid. So percent ionization equation is my hydronium that dissociated, that's at equilibrium, over my initial acid concentration times 100. So if it's less than 5, I can make that assumption. If it's greater than 5, then I have to do my quadratic formula. So let's learn how to calculate the Ka from the pH. So we're gonna set up a traditional ice table like how we would. So I find out the pH of a 0.1 molar formic acid solution is 2.38. So that is equal to my pH. So therefore I know my hydronium concentration at equilibrium, because that would be 10 to the negative pH. So if you get a pH and you know your initial concentration, you know everything you need to find the Ka. So here let's do my dissociation. So I have formic acid in water, breaks into hydronium and formate. So now what we can do is write out the Ka expression. So we write our formula, then the expression, so products over reactants. Since it's an acid, I've formed hydronium over my reactants, which is just formate, because water will be 1 since it's a pure substance. Okay, so now we can fill in our ice table as much as we know how. We know our initial concentration of formic acid, and I don't start out with any products. Now I can find my hydronium concentration from doing what we did over here, 10 to the negative pH. So I'll find out that hydronium is 10 to the negative 2.38, which is 4.2 times 10 to the negative third molar. So that's what I have here for hydronium at equilibrium. And since everything's a 1-to-1 ratio, I know that's how much I increased of hydronium. So I know my change. So that's how much I increase for my product here and how much I have at equilibrium. And then I can subtract that amount here for my equilibrium amount, negative third. Okay, so then plugging in, I can find percent ionization briefly. That will be my hydronium at equilibrium divided by my initial HA. So then I'll have 4.2 times 10 to the negative third divided by 0.1 molar times 100. That gives me 4.2%. So can I make the assumption? Yes, I can. So I can make the assumption that 0.1 minus 4.2 times 10 to the negative third is approximately still 0.1. Now, can you just plug it into your calculator because you know the number? Yes, absolutely. And honestly, I probably just would, but if you don't want to, for the sake of the assumption, you can just plug in your equilibrium amounts here, plug them into your Ka expression. So we'll have 4.2 times 10 to the negative third squared, because each of my products equals that, divided by 0.1. So that ends up giving us 1.8 times 10 to the negative 4. And if you did the denominator, the full amount, you would get pretty much the same thing. So now let's do something similar, but where we have 5.5 times 10 to the negative third molar of fluoroacetic acid. And that acid has a pH of 2.57. So we want to find Ka. So here's our little dissociation. Let's write our Ka expression, which is going to be hydronium times, I'm just going to call it A minus, that's the fluoroacetic acid, that's this whole guy, and then divided by the original acid. I'm just going to call it HA, so we don't have to waste time writing. Okay, so I'm going to fill in my ice table. So here I have, for my initial concentration, 5.5 times 10 to the negative third. I don't have any products. And I'm going to gain, actually I know how much hydronium I have because I know my pH. So we can find hydronium concentration by doing 10 to the negative pH. So we'll do 10 to the negative 2.57, and I get 2.69 times 10 to the negative third molar. So that's what I'm going to put here. That's what we gain for each of those. That's my X value. Great. And so then just gonna put that there. Oops. Okay, and then I'm going to subtract that amount from the other side. And you may be wondering, can I do the value here? Or can I make the assumption? I'm gonna assume not, because that's pretty close to my initial amount, but it doesn't matter because I can easily subtract that from my answer and get 2.81 times 10 to the negative third. So I did lose about half, and let's actually calculate that percent ionization by doing my hydronium at equilibrium divided by my initial acid concentration times 100. So I get 2.69 times 10 to the negative third over 5.5 times 10 to the negative third times 100. And I get about 49%. So yeah, this is a stronger acid. So let's find that Ka. So Ka, I'm gonna plug in 2.69 times 10 to the negative third squared, that's these values, divided by my equilibrium of the acid, 2.81 times 10 to the negative third. So then I get a K value of 2.58 times 10 to the negative third. So yeah, stronger acid has a higher K value. Okay, here's another one. We have niacin. It's an acid. It's a it's bigger acid. Has a structure. It's going to react with water to form my conjugate base and hydronium. Okay, so niacin has a concentration of 0.02 molar. And then I don't have any of my products. Okay, great. So let's find the Ka expression. So it'll be hydronium, products over reactants, times the deprotonated niacin over niacin. It's called HA. And so then I have a pH of 3.6. So once again, I could do pH equals, nope, I lied. We're going to do 10 to the negative pH equals hydronium. So I'll do 10 to the negative 3.26, and I get 5.5 times 10 to the negative 4 molar, and that is my my change. Great, so I'll put that in here, and then I'll also put that over there. Okay, so I'm gonna add that to both product sides, subtract it from reactant side. So then I go 0.02, subtract that number, and you get 0.01945. Okay, so now we can plug in Ka equals our products, and they're the same, 5.5 times 10 to the negative 4 square over my reactants, 0.01945, and we get 1.55 times 10 to the negative 5th. So weaker than the last one. Let's also find our percent ionization. And so that would be hydronium at equivalence over our initial acid times 100. So we'll do 5.5 times 10 to the negative 4 over 0.02 times 100, and we get it 100, and we have 2.75. So could we make the approximation? Yes, we could have, and we could have kept the denominator as 0.02. On these slides, we actually already did the percent ionization for fluoroacetic acid and niacin. So you can go back and look at those values. It was like a 49% for this one and 2.75% for this one. Okay, so next part, and we did this with the equilibrium chapter, is being able to calculate the pH. So we know an initial concentration. We know our Ka in this case. So I know Ka, I know initial, and then I'm going to set up an ice table, and then for my changes, I'm not going to know them, so I'm going to put X. So here, let's do it for acetic acid. I have 0.3 molar of acetic acid. Here's my dissociation. Let's write our Ka expression, and then I'll also tell you Ka for this, which we would find in a table, is 1.8 times 10 to the negative fifth. Okay, so Ka expression is products over reactants, so hydronium times acetate divided by acetic acid. Great. And so then we'll set up our ice table. So I have 0.3 molar here, 0 and 0. Then now I don't know my change. I'm going to do minus X and plus X. So 0.3 minus X and X. Great. So now we can plug that in. Now I know my Ka is 1.8 times 10 to the negative 5. That equals X squared now over 0.3 minus X. Now, before we could calculate our percent ionization and be able to know if we could make the approximation or not, but here we don't know the X value. So a general rule of thumb is if your initial concentration, if your initial concentration of your acid is greater than 1,000 times the Ka, then you can, and this is an ish, 1,000-ish, 800 sure, over 1,000 definitely, then you can make the approximation. So you can get rid of any plus or minus X's, get rid of them. So you don't have to do them. Okay, so what I'm going to do here is my 0.3 divided by my Ka to find my ratio. 8 times 10 to the negative fifth. So if I do 0.3 divided by that, I get 16,000. So I can, yes indeed, do this approximation. So what I'm going to do is down here, I'm going to just get rid of this minus X. And then we're going to calculate X, which is our hydronium concentration, and see what we get. So I'm going to take my 1.8 e to the negative 5 here, times by 0.3 on both sides to get that OGO, and then square root to get X by itself. So X, which is hydronium concentration, look at my products here, right, is 2.32 times 10 to the negative third molar. So now let's check. Remember my hydronium percent ionization equals hydronium divided by initial acid times 100. So I'll do 2.32 times 10 to the negative third divided by 0.3 times 100. And I get 0.7%. So yes, that is very small, so I was good to make the approximation. So my ending answer here for hydronium is this. So then I want to find the pH. So I'm going to do negative log of hydronium equals pH. So I'll take negative log of 2.32 times 10 to the negative third, and I get a pH. Oops. pH equals 2.63. Okay, now let's do the pH of hydrocyanic acid. We have 0.2 molar. And if we go look back at that chart, I can see hydrocyanic acid has a Ka that equals 4.9 times 10 to the negative 10. So very, very weak. So we're going to write our dissociation. Hydrocyanic acid and water gives me hydronium and cyanide. So I have 0.2 molars of that and no products initially. Now I'm going to minus X from reactants and plus X to the products. Okay, now let's set up our Ka expression. It's going to be products over reactants. Oops, okay. And my Ka is 4.9 times 10 to the negative 10 per the book. And then I'm going to have X squared over 0.2 minus X. So can I get rid of minus X? Let's double check. We'll do the math. I can already tell this is a super tiny number. So I already know I can, but I'm going to take my initial concentration here, so divided by that. So I'll get 0.2 divided by 4.9 times 10 to the negative 10. And I get 10 to the 8. So very, very big. So remember, if it's greater than about 1,000 or greater, then you're good. So 10 to the third, we are good to do the approximation. So I don't have to write minus X like that. I could just leave it like that. So then to solve for X, I'll divide by 0.2 on both sides, square root. So we get 0.2 times 4.9 times 10 to the negative 10, square root. And I get X equals 9.9 times 10 to the negative 6 molar. That's my hydronium concentration. So remember, pH is a negative log of that. So I'm going to do negative log of that number. And I get my pH equals 5.00. Great. So we love it when we have small Kas because we're in a high concentration of acid, high-ish, because then we're able to do that approximation. Okay, let's do it again. We have hydrofluoric acid dissociating in water. So we're going to get hydronium and fluoride. And I happen to know that the Ka is 6.8 times 10 to the negative 4 for hydrofluoric acid. So let's do our approximation. We're gonna see if we can do our approximation. We're gonna do 0.1 divided by 6.8 times 10 to the negative 4. And that gives me 147. So we cannot do our approximation because that's not a very big difference. Okay, so we're gonna do our ice table. And I have 0.1 molar for hydrofluoric acid, no products, minus X for reactants, plus X for products, 0.1 minus X, and X. So then I'll set up my Ka expression, products over reactants. So here's my acid. So then my Ka is 6.8 times 10 to the negative third equals X squared over 0.1 minus X. And I know you hate it, but it's okay because we're going to solve it the long way and it's okay, it's good for us. So we're going to distribute on both sides. 0.1 minus X cancels out. So I get X squared equals 0.1 times the products. Oops, that's negative 4. Okay, so then I'll have 6.8 times 10 to the negative 5 minus 6.8 times 10 to the negative 4x. I'm going to move these guys over, both of them that way. Doesn't matter, but which way you go, x squared plus 6.8 times 10 to the negative 4x minus 6.8 times 10 to the negative 5 equals 0. Okay, when we solve for that, we get our X, which is equal to hydronium, equals 7.9 times 10 to the negative 3rd molar. So then if I want to do my pH, I'll do negative log of hydronium. So pH equals 2.10. Now the problem also asks for percent ionized, so let's just do that. Remember, it's going to be H3O plus over our initial HA times 100 for percent ionization. So I'm going to have my hydronium, which I just found, 7.9 times 10 to the negative 3rd, divided by 0.1 times 100, and that's 7.9. So we were good to not do the approximation because this is higher than 5. So we're good. And so this a little kind of anecdotal way I do it usually works out pretty well. So just looking at strong and weak acids, we know that strong acids completely dissociate because their hydronium concentration equals their initial acid concentration. And weak acids, their hydronium at equivalence is much less than their initial acid concentration. And so that impacts their conductivity. So strong acids are gonna, because they break into ions completely, they have a higher conductivity. And it affects their rate of reaction. So here we have acid, hydrochloric, and acetic, both 1 molar. But notice hydronium concentration for the 1 molar hydrochloric is 1 molar. But for our acetic, it's only 4 millimolar. So a lot smaller hydronium concentration. So when I put a piece of metal like magnesium in there, the strong acid is going to react a lot faster than our weak acid. Now at the end of the day, they're both going to go to completion, but our weak acids are just going to go a lot slower than our strong acid. So if I have a mixture of acids, the general rule of thumb is you ignore the contribution from the weaker acid. It's not going to contribute very much hydronium compared to the stronger ones, so we're not going to worry about it. Generally, if I have a strong acid plus a weak acid, then the strong acid's complete ionization will outweigh the weak acid's amount of hydronium that it'll have at equilibrium. So it's not going to have very much of an impact. It will also shift the equilibrium back to the left via Le Chatelier's principle, so it even minimizes it even more. If I have a mixture of 2 or more weak acids, we're basically, again, only going to consider the stronger acid, especially when it's significantly stronger. And by significantly stronger, the general rule of thumb is 1,000 times stronger. So if 1 Ka is about 1,000 times the Ka of another one, then we're going to not worry about the smaller one. So if I have hydrofluoric acid, I'm going to write that dissociation, HF plus water goes to hydronium and fluoride. And that Ka is 6.8 times 10 to the negative 4. And then I have hypochlorous acid and water. That Ka is 2.9 times 10 to the negative 8. So these are about 10,000 times different. So basically, hypochlorous acid is so much weaker that we're not even going to think about it. So we just treat it like a regular old weak acid problem with hydrofluoric. And we already solved one like this, so we can do it again. So why not? So again, just going to ignore the weaker one because it's barely going to do anything. So we'll do HF. Let's write that guy. There's my reaction. Set up an ice table. 0.3 molar minus X. I don't have any of my products. So then my Ka is hydronium times fluoride over the acid. So that's 6.8 times 10 to the negative 4 equals X squared over 0.3. Now can we do it? Let's check. 0.3 over 6.8 times 10 to the negative 4. Well, this is about 500. So I'm gonna try it. Let's just see. Let's times both sides by 0.3. Let's try the approximation. And then square root. And we'll check our percent ionization to see if the rule works. That is kind of the thing you get to do, is just check and see. So when we make the approximation, we get X equals 1.43 times 10 to the negative 2 molar, which is hydronium. So let's divide it. Let's just try percent ionization. So it'll be, again, hydronium over the acid times 100. So at equilibrium initial. So 1.43 times 10 to the negative 2 over 0.3. And that gives us 4.76. So pretty close. We're gonna just call it a good day. When in doubt, you could always do the quadratic formula to give you the most accurate. So then pH equals negative log of hydronium. So negative log of 1.43 times 10 to the negative 2 is 1.86. Great. Okay, so we have practiced a lot with weak acids. We're now going to do it with weak bases. Guess what? Basically the same thing. So nothing too crazy. I hope that you're getting the hang of it.